Good evening, everyone. Thank you once again for attending one of the last sessions of NANOG on a Wednesday. I very much appreciate that. My name is Tim Fayola, and I'm going to talk to you today about network modeling, open sourcing the network model, and the value that provides when you model your wide area networks. Okay. I am here as an independent person. I am an automation and network modeling enthusiast. So here's the agenda. We're going to first define the problem statement. We're going to take a look at why network modeling is strategic. We're going to define what a network model is, what it does, the need for open source tools in this space. We're going to talk about PyNTM and why it's helpful, and a little bit of a spoiler alert. PyNTM is a network modeling engine. Okay? We're going to talk about the PyNTM features and roadmap that it currently supports, and then where we're looking to take it. We're going to discuss if and how PyNTM can help you right now as it is, next steps for getting to know PyNTM, and then we're going to talk about a demo. Understanding the WAN is hard. It's very difficult. In a big meshy network, it becomes really difficult to understand how your network's going to react to a failure. Are you going to saturate links? Do you have enough capacity somewhere? Do you have too much capacity somewhere? It's hard to understand in a big meshy WAN how a failure might impact utilization in other parts of the network. So because it's such a difficult problem, there's often use of like educated guessing and general rules of thumb for learning, for augmenting and growing the network. Okay. So you take an IGP, a meshy IGP WAN, and then you throw auto bandwidth LSPs on top of it. It becomes even more difficult. The traffic any given link would handle can change throughout the day, the week, the month, the year. Bypass LSPs can have very non-intuitive impacts when triggered. Auto bandwidth LSP behavior is often non-deterministic. And one of my favorites is you add capacity in one part of the network and you change the behaviors of an LSP in a different part of the network. That's always one that is difficult to understand if you're seeing it in your network itself. Okay. So an aggravating factor here is WAN circuits are expensive. They're not always available for the routes you want. And when you can get one at the right price, it takes a long time, sometimes months, to turn up that new capacity. So you have to be ahead of the game here. So let's talk about modeling. Network modeling will give you insight into your WAN's behavior. Modeling gives you a very unique, data-based understanding of how your network's going to behave during failover, during changes in your traffic matrix, and other changes in your topology, such as adding or changing your RSVP LSP mesh. And speaking of that, modeling is a great way to understand how to read your LSP mesh and what it might be telling you about needing to add capacity. So this insight from WAN modeling is strategic. This is why. It lets you It helps prevent you from overbuilding WAN links, which strand your capital, or not building enough capacity in your WAN links, which increases your network risk. This is strategic value. So these are some roles that a network model will help with. CAP planner, network engineer, anyone planning or conducting a maintenance, or anyone with a general interest in network performance. All these roles can benefit from using a network model of the WAN. So let's look at a network model. Two main input components in a network model. There's the traffic matrix. And the traffic matrix, many of us have seen them before. It's a way of describing how much traffic is going from one node in your network to a separate node in your network, and how much traffic that is. And I'm going to show an example on the next slide, so I won't go too much into it. The other piece is the topology. Your topology includes your layer 3 nodes, your circuits between your nodes, your shared risk link groups, your RSVP LSPs, and you can throw a lot more into the model as well, depending on what your use cases are. But these are some very common ones. Another common one that's not on here is the layer 1 underlay. Okay. The traffic matrix. It's going to vary over time. There's not one traffic matrix for your network. There are many traffic matrices over time for your network. This is one of the toughest parts of modeling, is getting a good input traffic matrix. It's tough. It can be tough. You have to have the right resources to do it. But you need to do it because understanding your matrices for your network, you need that to do truly effective engineering and planning of your WAN. Because if you can't even define the problem, it's hard to counter the problem and solve the problem without that knowledge. So in this sample traffic matrix here, laser, this is a very simple traffic matrix, but you're sourced from node A, your traffic destined for node C, oh my gosh, look at that. It's 120 megabits per second. That is the magnitude of the traffic demand. From node A to node C, 120 megabits per second of traffic. It's a pretty simple concept. And one common question I get in WAN modeling is, hey, what if I make a BGP change or a policy change? Can you model that? No. The traffic matrix is a product of all those policies, and let me back up. It's a product of all your BGP policies and any other policies that will affect traffic. But in the end, the traffic matrix is just traffic going from one part of your internal domain to another part via IGP. That's what a traffic matrix is. So all those things are essential to forming your traffic matrix, but in the end, the traffic matrix is something like this. From here to here, I have this much traffic. Okay. So network modeling provides simulation capability. And what is a simulation? Apply your traffic matrix to your topology. The way the traffic routes is widely understood, so you just simply route the traffic demands the same way your network would. This gives you data on the network state for the simulation. So on a given day, you would have different traffic matrices for your network, and you would have different network states you would model throughout the day for your network to understand how your WAN will behave different parts of your day if it encounters a failure or a topology change. Okay. Click. All right, there we go. So without modeling, rules of thumb are often used for WAN engineering and planning. Rules of thumb are general. One I hear very often is, we augment circuits when they reach 50% capacity automatically. Okay. Since it's a general rule, you might be overbuilding or underbuilding based on that policy. General rules don't protect you necessarily against failures you are or should be interested in. They don't help define the problem. It's just a rule you blindly follow. They may have unintended consequences because they are general. So a simulation gives you insight as to how your network's going to behave during a failure event, or a change in the traffic matrix. If you're planning a big augment, if you're expecting a new customer turnup, that's going to have a lot more traffic in 2 months. Model it, see where you're vulnerable, get ahead of it. And again, it gives you insight as to your LSP mesh behavior. So modeling can show you, it can uncover vulnerabilities in the WAN. You run a bunch of different scenarios and realize we're exposed here. We have risk on this link that we didn't know before. That's non-intuitive, but it's there. Modeling can help uncover what you should be interested in as far as failures in your network. And if you want to do more sophisticated analysis, for instance, I want to plan a greenfield network. I want to optimize this network for low cost. You need some type of simulation engine under the hood to run the scenarios and give you the optimal solution for what you're trying to do. A model is foundational for strategic planning of your network. A few more benefits. We covered the capital. You can efficiently allocate your capital. Don't overbuild or underbuild. Expose events you care about. Simulations produce a ton of data about the state of the network for the given conditions you're simulating. This is a great way to be more fact-based or data-driven, but for real this time, about what you do with your network. At a minimum, modeling gives you the ability to make more informed, educated decisions. You don't necessarily need a sophisticated modeling setup to get value from this network modeling. For instance, if you use rules of thumb generally, okay, model out your rules of thumb. Are you overbuilding? Are you underbuilding? A simple use case like that, test our general rules of thumb, it can start to provide value for you. So here are some use cases for network models. Understand your topology. Understand your failover by modeling failures. Understanding where it makes sense to augment. How do changes in the network affect my traffic flow, my traffic spread? RSVP implementations if I want to modify my mesh or add a mesh. And again, expose what failures should I be paying attention to. You might uncover some blind spots. So we need to make this more accessible. We need open source tools that allow a programmatic approach to network modeling and simulation. Specifically, I would like to see an open source modeling engine, which PyNTM, laser, of which PyNTM is one. So it's an open source modeling engine. The other part is open source tools to create reasonable traffic matrices. My friend Paolo has a good one, PMA-CCT, that's very helpful. A nice to have would be an open source GUI for visualization in case a human wants to interact with the network model. So what is PyNTM? It's the Python 3 network traffic modeler. It's open source. It simply applies a traffic matrix to a topology to route traffic as the network would. Under the hood, we're using network X to get the path information for the topology. And I can't say enough good things about network X. I love it. And without network X, there's no PyNTM, there's no open source modeling engine. It is a great module. But there's more to modeling than just understanding your paths, and we're going to talk about that. So what the value PyNTM provides is it takes your network X paths and it builds infrastructure around them to model a network-specific state. And what does that mean? So let's look at just kind of what we've got going on here. In PyNTM, your traffic demand paths and RSVP paths, I get those from network X. Then I use the constructs in the engine to derive interface utilization, to model reserved bandwidth for interfaces, and to model the actual interfaces that the traffic egresses from source to destination. So in other words, network X provides the path, but then PyNTM will map the traffic to an LSP, the LSP to interfaces, and then derive the interface utilization caused by the demand on the LSP on the interface. That's what PyNTM provides as a simulation engine. Okay? So before I go any further with this, I realized after showing this to a friend, I wasn't clear. These numbers up here represent traffic egress in the interface from left to right. So you have 12 megabits per second ingressing the topology at node A. And then what I'm showing here in these pictures is how much of that traffic goes on each interface, egresses each interface from source to destination. So where I'm going with that is traffic spreads. You can't model utilization from a certain demand just by taking the unique paths and splitting the demand by the unique paths and modeling that traffic across the interfaces. It doesn't work all the time. For instance, in this example here, we have two of the paths through the network have a common interface from A to C. In an end-to-end load balance scenario, you're going to get 8 megabits per second of traffic on that link right there, and 4 going up top. This is not how IGPs necessarily behave. In some corner cases, like if you have a big, exceptionally huge flow within this, you might get the elephant flow where it all hashes out onto one link and kind of throws you off. But in this example here, let's just assume there's many flows, none of them is abnormally large, and we're getting good hashing. So just take note of this traffic spread. It's an end-to-end traffic spread for this demand. Let's talk about what really happens. What really happens in an IGP is you use hop-by-hop load balancing. So in hop-by-hop load balancing, you get these splits. So this looks very different than the traffic spread from the end-to-end load balancing. The point of all this, traffic modeling is more than just understanding your paths. You have to understand how your traffic's gonna split upon each path and model that behavior. So why is it helpful? It leverages your path information from network X and gives you network state specific context. And PyNTM APIs, they allow for a programmatic network modeling capability. So you don't have to have a person with a GUI clicking and doing all this stuff to do hundreds of simulations. You can program the simulations, walk away, and come back and look at the data, see what it's telling you. PyNTM allows users to easily modify the topology of a network and determine alternate network state based on that change. For example, failing a node, adding a new circuit, adding LSPs. You can easily do that in PyNTM and then see what does it do? What's my network doing under those new conditions? And it's specifically designed to easily relate related objects in the model. For instance, traffic demands right on LSPs, which have a path, which transit interfaces, which are on nodes, which source traffic, which sync traffic. You can mine all this information easily with PyNTM from the model to understand stuff that might not be intuitive about what your network is doing. Features and roadmaps. So currently version 1.5, that's the most recent version of PyNTM out there. It supports IGP routing, RSVP, LSP full mesh, and within that, it supports auto bandwidth LSPs where they will adjust to reserve as much bandwidth as they need and can. And it also supports manually assigning a bandwidth to an LSP. Supports shared risk link groups. And so right now, it currently supports modeling a single link between layer 3 nodes. For many use cases, even if you have parallel links between multiple nodes, in a lot of use cases, from a modeling perspective, it makes sense to model those as a single link. You don't necessarily have to model them as separate links, depending on your use cases. So right now, we support a single link. So if you'd have multiple links, you would combine them to model as a single link, at least right now. Because we meaning I, but hopefully we, at some point here, are accepting feature requests and or pull requests on GitHub. There's 3 open feature requests that I've got so far. One is for IGP shortcuts for RSVP LSPs. One is for multiple links between layer 3 nodes, and I'm currently working on that. Interesting problems to solve with coding. I'm trying to figure out if there's a performance penalty in the modeling engine having multiple links between two nodes, because it necessarily means there's more processing to figure out which link you'd be taking between nodes. But anyway, I'm looking into that. Top people. And the third feature request is assigning a manual cost to an RSVP LSP. Those are the three that are open right now. Possible roadmap features that I've thought of. These are some of them. It's helpful to get feedback from the community, though. These are ones I think are valuable, but I can't tell. So if this is something that's interesting to you, I would like to understand, even if you're not going to use PyNTM, what you would want to see in an open source modeling engine. A couple other ones that I thought of just as I was going along is incorporating a database into the model object to quickly retrieve data. I think that would improve performance, because right now the simulations generate a ton of data, and I'm not necessarily keeping all the data right now. A lot of it I am, but some of it I'm rederiving again when you ask, when there's a certain call. A database might help in that area. So setting up a database to do something like that would be super helpful. And regional RSVP meshes. And again, excuse me, I'm always open to performance improvements and optimizations. If you happen to be good at finding optimizations in code, I would love to hear about it, because right now, simulating LSPs is very expensive, because you have to basically simulate them one at a time, converge the model, simulate the next routing, converge the model, because one LSP's path is dependent on how the other LSPs before it route. So LSPs are expensive. So that is where I'm looking for more optimization right now. That being said, I'm getting pretty good performance, but it could definitely be better. Can PyNTM help you right now? So generally, you have two options. And there's a secret third option, which is called build your own, but I'm not going to cover that. But you have commercial options, and the big ones out there are Cisco has a product, Juniper has a product. I think Aria Networks is still around. They have a product. Those are your commercial options. Then you have PyNTM. And what I'm doing here is I'm just drawing out the differences here. Clearly, with the commercial options, you're going to have cost. They cost money. PyNTM is just there. It's free. Both have APIs for programmatic modeling. At least most of the commercial options do. One thing about the commercial options that can't be undersold, I think it provides great value for the commercial options, is a lot of them will create a traffic matrix for you. So if you can't create your own traffic matrix, you probably want to go the commercial option route, because they will often create one for you, and that value there is huge. The commercial options have sophisticated UIs for visualization, which PyNTM does not. And then there's the open source. We're open source. The vendor is not. So you're not as dependent on the vendor with PyNTM. So this is the call to action slide. This needs to be a thing now. Python is mature. Python is prevalent in the networking community. The need for modeling is huge right now, because more and more networks are hitting scale constraints, where there's capital budget constraints, there's WAN link constraints, there's people constraints. There's just not enough to keep up with how to grow the WAN. You need to grow it smartly, not just with rules of thumb. More reasons why this should be a thing. The capability for basic modeling is very mature. These commercial products have been around for 17-ish years. Mature technologies can and should be modularized. So for instance, you can have one app to create a traffic matrix, maybe PMA CCT. One app to model that uses the traffic matrix, maybe PyNTM. Okay. So who is this for? If you have access to a reasonable traffic matrix, if you have coding skills for Python, if you don't want to rely on external vendors, and oftentimes that's a cultural thing within a company. If your WAN is IGP only, or if it's IGP plus full mesh RSVP, you can start using it now and at least kick the tires. I love the feedback. Otherwise, look, I'm still adding features. I have some feature requests that were submitted. I would love more. I'd love to see what the needs are of the community to open source the modeling engine. Okay. Next steps for you if you are interested. PyNTM is downloadable as a Python package from PyPy. Be sure to do a pip3 because this is Python 3. The GitHub full repository is super cool. It gives you access to sample scripts, and it gives you access to some beta features, including an interactive visualization that's good at small scale, and a simple user interface to help a human explore the model topology. There's some free training modules which I recently published. Those are on the wiki page for the repository. We have read the docs. Doc strings are real. I've done them. And if you feel you can enshrine network behavior in code, feel free to contribute. I would love the input, the feedback, and the help. So, quickly here, demos seem like a good idea until they don't. I had to record a demo to do, but it was terrible on these screens in this big a room, so I cowboyed a bit this morning, and I'm just going to show screenshots. The point of this, of showing a demo and now the screenshots, is just to show you that using PyNTM programmatically is a real thing. It can be done. So we'll cover that as we go. So how are these looking? Oh, pretty good. Okay. So the first thing we're doing here is this up here. This is just some boilerplate stuff. What we're doing here is we're creating a model object by using a class call and loading the network data, the topology information, and traffic matrix for that matter, from a CSV file. So now you have your model loaded. You need to get your simulation data. So you need to run an update simulation. This call right here will actually do the routing of the LSPs if present and of the demands. So we've loaded the network. We have our model. It's converged because we updated the simulation. This is one of the beta features. It's this interactive network graph, and it's beta because it's not core. It's just kind of a augment that I did to help in training, really. So this is the call to create the interactive network graph. And don't worry about trying to read the information on this graph. But what this does is it creates a locally served interactive map powered by MPLD3, which is a super cool Python plugin. If you haven't messed with it, it's awesome for data visualization and interaction from Python. So what you should note here is that we're showing there's a interface utilization legend on the side here, and there's two interfaces, the purple ones, that are over 100% utilized for egress traffic. So I'm going to skip this. I'm running out of time. So we've converged our model. Hey, let's look at interfaces that have over 90% utilization. It's just a simple for loop. Grab the interface objects, look at the utilization. If it's over 90%, print some information about the interfaces. So we have the interface name, the source node, and then the utilization. So we have two interfaces that are over 90% utilized. We're going to fail an interface now. So I'm going to do a call to grab an interface from the model. And here's the repr for the interface. And here I'm doing a call, a true-false call. Is this failed? It is not failed. It is false. So, given that it's operational, let's fail it. So you do a fail interface call from the interface object, update the simulation. Okay, this might be a bit of an eye chart. So what I did is I just did a for loop, grabbed all the interface objects, and printed the interface utilization for each interface. Let's look at the highlight. So we failed the interface from A to B. So that's down, no surprise. But the interface from B to A also went down because a circuit needs two interfaces to stay up. So the circuit failed, the other side failed. And the other interesting piece of information here is our utilization on A to D went to 164%. Wow! What's causing that utilization? Here's the quick visualization. Failed circuit, interface we're looking at. It's very saturated. So this is just me showing off how I have doc strings. They're real, they're a thing, necessary. What I did here is I'm grabbing the demand. So what is driving that 164% utilization on that interface? Let me grab the traffic. These are the demands that are egressing that interface, causing that 164% utilization. So now you know what traffic's affected by that failure. You know what demands are dropping traffic. Okay, so real quickly here, because I'm about 1 minute over, I think. What I did here is I grabbed a demand from the model, from the demand from A to B, and what I'm doing here is I'm using the path call from the demand to tell me, hey, what path or paths does this demand take across the network? And there are two equal cost paths. One from A to D and D to B, and one that's got 3 hops. Here are those paths kind of visualized. Node A, D to B, and node A to D to E to B. This is not always intuitive to do in a big network. You can do this with PyNTM. Okay? That's the point here. All right. That wraps it up for the talk. If there's any questions, I'm happy to take them now, or we can talk later on as well. Okay. Looks like we are done. Thank you. Thank you.